In this presentation, I'll be explaining what is Schmitt trigger, or that's also called regenerative comparator. It is one of the application of comparator. Schmitt trigger, or it's called the regenerative comparator. This is a circuit diagram of a regenerative comparator or Schmitt trigger, in which op-amp is the signal that is given. Vi is the input signal that is connected to a non-inverting terminal through a resistance. And here these two resistances, that is feedback resistances, are there, R1 and R2, and here output voltage is either it will be plus Vsat or minus Vsat, depend upon the relative magnitude of this one. And at this end we are applying a reference voltage. Therefore here this voltage equal to reference voltage, and this voltage will be either plus Vsat or minus Vsat, and then the voltage at this point is tapped, and that is given as a plus terminal. It's a positive feedback circuit in which the input signal is applied to the non-inverting terminal. Therefore, this is a circuit diagram of a Schmitt trigger. Therefore, if positive feedback is added to the comparator circuit, then gain can be increased greatly. Consequently, the transfer curve of the comparator becomes close to the ideal curve. Or here, if you see the closed loop gain of an op-amp, it is equal to open loop gain divided by 1 plus or minus open loop gain into beta. Therefore, this either plus or minus, that is depending upon whether it's a negative feedback or positive feedback. If it is a negative feedback, it will be plus sign. If it is a positive feedback, it will be minus sign. Since it is a positive feedback, in this case, the gain is given by AOL divided by 1 minus AOL into beta. Therefore, this is the gain of this amplifier. Gain of the positive feedback amplifier is given by open loop gain divided by 1 minus open loop gain into beta. And beta means called the feedback factor. Here, the ratio of this R2 divided by R1 plus R2, that is called the feedback factor. Therefore, this product, that is the feedback factor into the open loop gain, that is what we call it as the loop gain. AOL into beta is adjusted to unity, and that if you make this AOL into beta, that is given as unity, then you can see that when the gain with feedback is equal to infinity, because 1 minus 1, 0, that will become infinity, meaning that this results an abrupt transition from extreme values like plus or minus Vsat. It can be, that is, we have to make this the product AOL, or is open loop gain into beta to unity. Then the transition from plus Vsat to minus Vsat, that will be taken abruptly if this condition is being satisfied. Now, in practical circuits, rather than making AOL beta equal to unity, it is slightly more than 1 is made. In practical circuit, it may not be possible to maintain the loop gain, that is AOL into beta, exactly unity for a long time because of the supply voltage variation as well as temperature variation. This can be keeping 1 is very difficult. In that case, normal case is that this loop gain is made slightly less than, greater than 1. So a value of greater than unity is chosen, so that will be working as a positive feedback circuit, in which transition from plus Vsat to minus Vsat or minus Vsat to plus Vsat takes place suddenly. Therefore, this is a circuit diagram of a Schmitt trigger. Let us analyze that circuit diagram in the next slide. Continuing the Schmitt trigger circuit, same circuit is shown here. Input resistance say R3 is connected, that is input voltage is R1 and R2 is the feedback resistances. Output voltage V0 either plus Vsat or minus Vsat, and this is the reference voltage applied. Therefore, this is a Schmitt trigger circuit in which the circuit can exhibit a phenomena called hysteresis that we will be seeing later. A hysteresis is that is, for example, just to explain the hysteresis, say this is the input voltage that is given at this point. Vi is equal to sinusoidal voltage is given, and there are two reference voltages like upper threshold voltage and lower threshold voltage, VUT as well as VLT, meaning that if input voltage is going more than upper threshold voltage, if the input voltage is more than the upper threshold voltage, then the output will be changing from minus Vsat to plus Vsat to minus Vsat. The output is changing from plus Vsat to minus. Again, if the input voltage is, even though here if you see that input voltage is going less than VOT, it won't change at that instant. Rather than if the input voltage is going less than another limit we call it as lower threshold limit, that is VLT. If only when the input voltage is going less than the lower threshold voltage, again the transition from minus Vsat to plus Vsat is taking place. Now for a slight hysteresis that produced, that is here to change from plus to minus, it should be more than upper threshold voltage. To change from minus Vsat to plus Vsat, it should be less than another voltage, that is called lower threshold voltage. And the difference of these voltages are called the hysteresis bit, or that is we call it is equal to the difference of upper threshold voltage as well as lower threshold voltage. That difference we call it as hysteresis bit. That is meant by the hysteresis, that the input is given to the non-inverting terminal. We are giving, sorry, input is given to the inverting terminal, because minus terminal, that is given the input, and the feedback is given. This feedback is given to a non-inverting terminal. That is feedback, it's a positive feedback. Therefore, the feedback is applied to the positive input terminal. The input voltage Vi triggers the output voltage V0 every time when it is exceeding a certain voltage levels. That is, if input voltage is exceeding the upper threshold voltage VUT, then output is changing from minus V plus Vsat to minus Vsat. Again, when input voltage is going less than the another voltage limit, that is lower threshold limit, again the transition from minus Vsat to plus Vsat is taking place. Therefore, these voltage levels, that is upper threshold voltage and lower threshold voltage, these are called VUT as well as VLT. That we can derive in terms of this reference voltages, Vsat as well as R1, R2. You can derive the equation for upper threshold voltage and lower threshold voltage, and then you can calculate what is the hysteresis width, which is nothing but the difference of these voltages, that is called the hysteresis width. Now continuing the Schmitt trigger configuration, in which we have to calculate what is the upper threshold voltage and what is the lower threshold voltage. And here, as I told you, the output of comparator can be either plus Vsat or minus Vsat. There are only two extreme cases. It can be either plus Vsat or plus biasing voltage or minus biasing voltage. Now, when it is output voltage, you could assume that output voltage equal to plus Vsat. When this voltage equal to plus Vsat, what is the voltage coming at this point? Because this voltage equal to V reference voltage and this voltage equal to plus Vsat. Now, what is this voltage? There are two voltages coming, and you have to calculate what is the voltage at this middle point. In order to calculate this one, you have to apply the superposition theorem. That is, when plus Vsat is present, you have to ground this point. Then you have to calculate what is this voltage. Then when V reference is present, you have to ground, you have to consider as a ground voltage here, and then you have to calculate what is this voltage. When both inputs are coming, then you have to add these two voltages so that you will be getting what is the voltage when both inputs are applied. That is the superposition theorem. Therefore, suppose the output voltage is equal to plus Vsat here, and the voltage at plus input, that is this point, can be calculated or that can be determined, obtained by superposition theorem. That is, when plus Vsat is coming, what is this voltage, which is equal to V, and then at that point this is grounded. Therefore, it is equal to plus Vsat divided by R1 plus R2 into R2. That is this one. Next one. When V reference is present, you are assuming that this is grounded. Now this voltage is given by, it is equal to V reference divided by R1 plus R2 into R1. It is into R1. You have to note it. It is equal to into R1. Therefore, when both are present, the corresponding voltage is the addition of these two voltages. That is a superposition theorem. Therefore, this is the voltage when both inputs here plus Vsat and V reference voltage are present. That is this voltage. And this voltage we are defining as the upper threshold voltage, VUT. This is a VUT. Therefore, if the input voltage is less than the upper threshold voltage, output voltage equal to plus Vsat. Meaning that if the input voltage is less than the upper threshold voltage, the output voltage remains at plus Vsat. That is, we have seen here, if you see the limit of that one here, if the input voltage is less than this upper threshold voltage, output voltage equal to plus Vsat. That is the point. Therefore, here As long as input voltage is less than the upper threshold voltage, the output voltage remains constant at plus Vsat. If the input voltage is just greater than this threshold voltage, then output voltage will be switching from switching from plus Vsat to minus Vsat and remains at this level as long as the input voltage is more than this is equal to VLT, actually lower threshold voltage. Until that point, the output voltage is remain as minus Vsat. That is clear from this one. In this case, it is changing as the input voltage is going more than upper threshold voltage, that is changing to minus Vsat, and that will be continuing until the input voltage is just crossing the lower threshold voltage, that is here. Therefore, like that one, you can calculate what is the upper threshold voltage. In order to calculate the lower threshold voltage, when this is equal to minus Vsat, what is the voltage coming at this point? When it is equal to minus Vsat, again you can apply the superposition theorem and you can calculate what is the voltage that is coming at the plus input terminal. Therefore, here it is equal to minus Vsat divided by R1 plus R2 into R2, then plus, when V reference is present, this is grounded. V reference divided by R1 plus R2 into R1, that one. Therefore, this is the equation 2, which is representing the lower threshold voltage, and equation 1 represents the upper threshold voltage, and the difference of these one, VUT minus VLT, that is what we call it as hysteresis with VUT minus VLT. That is, if you subtract these two, this one and to this one, or here, it will be getting twice V reference divided by R1 divided by R1 plus R2. That is the hysteresis width. Again, continuing the Schmitt trigger circuit here, same circuit in which we have derived the equation for the upper threshold voltage, which is equal to Vsat into R2 divided by R1 plus R2 plus V reference into R1 divided by R1 plus R2. Similarly, we derived the equation for the lower threshold voltage, which is equal to minus Vsat into R2 divided by R1 plus R2 plus, again same thing, V reference divided by R1 plus R2 into R1. Therefore, these are the equations corresponding to the upper threshold voltage as well as lower threshold voltage. And in order to calculate the hysteresis width, we are subtracting this. We can get what is the VUT minus VLT, or if you subtract this one from this one, or 1 minus 2 will give twice R2 divided into V reference divided by R1 plus R2. Therefore, this is the hysteresis width. Now to just to explain the hysteresis width, just to as a hysteresis diagram, it is shown here. You can see that one is the transition from here. This is a plus Vsat, and here this is a minus Vsat. Therefore, that is if the input is going the upper threshold voltage. If the input is going upper threshold voltage, it is changing from plus Vsat to minus Vsat. Then when input voltage is going less than the lower threshold voltage, again it is changing from minus Vsat to plus Vsat. Therefore, there is a hysteresis is taking place, and this width we call it as hysteresis width, which is the difference of upper threshold voltage VUT minus VLT. That is equal to twice R2 into Vsat divided by R1 plus R2. That is clear from this one. When input voltage is going above the upper threshold voltage, output is changing. That is, output is changing from plus Vsat to minus Vsat, plus Vsat to minus Vsat, and that will be continuing to minus Vsat until when that will be continuing to until when input voltage is more than that is the input voltage is going less than that is going less than the lower threshold voltage. That is when input voltage is going less than threshold voltage. Again, the transition is taking from minus Vsat to plus Vsat. Here it is changing from minus Vsat to plus Vsat. That is why you are getting an output perform like this one. And this is the hysteresis taking place. That is why it is called a regenerative comparator, or this bit we call it as hysteresis bit. Therefore, this is the equation for the upper threshold voltage, and this is the equation for the lower threshold voltage. And if the input voltage goes less than the lower threshold voltage, output will be changing from minus Vsat to plus Vsat. That is this instead, minus Vsat to plus Vsat, and this is the hysteresis width. Now continuing the Schmitt trigger circuit. This is the circuit as already we have seen. Input voltage is there, and this is a reference voltage, and this is the either it will be plus Vsat or minus Vsat. If it is plus Vsat, the corresponding voltage is equal to upper threshold voltage, and if it is minus Vsat, corresponding voltage coming at this point is equal to lower threshold voltage, and the difference of this one is called the hysteresis bit, which is equal to twice V reference into R1 divided by R1 plus R2. That is, now if you assume that rather than applying a voltage reference voltage, it is grounded. Assume that you are grounding this point. If you are grounding this point here, this will become 0. Therefore, this part will become 0. Again, this is reference equal to 0, means this part will become 0. Meaning that VUT equal to Vsat into R2 divided by R1 plus R2, and VLT equal to minus Vsat into R2 divided by R1 plus R2. Meaning that upper threshold voltage is equal to minus of lower threshold voltage. VUT equal to minus VLT. We will be getting VUT equal to minus VLT, which is equal to Vsat into R2 divided by R1 plus R2. This will be happening when this is grounded. Rather than applying a voltage at the reference voltage, if you ground this one, then upper threshold voltage is equal to minus of a lower threshold voltage. Now, if you consider here, assume that this is the input voltage that is applied to here, and if, for example, if it is equal to say 5 sin omega t, maximum is equal to 5. Now, if you apply here plus 3 voltage, or say assume that this is equal to plus 2 volt, here this is equal to plus 2 volt, then lower threshold voltage is also minus VUT. This is equal to minus 2 volt. That is happening when ground voltage, if you are grounding this one, then VUT is equal to say plus 2 volt and VLT will be equal to minus 2 volt. Again, if you apply this working of this, Schmitt trigger, if the input voltage is going above the upper threshold voltage, output is changing from plus Vsat to minus Vsat. That is, at this instant, it is changing from plus Vsat to minus Vsat. Then next transition is taking place when input voltage is going less than the lower threshold voltage. That is at this instant. Again, that is changing from minus Vsat to plus Vsat. Therefore, this is the output waveform and this is the input waveform, and these are the reference, these are the upper threshold limit as well as lower threshold limit, provided you are grounding this point. Therefore, when you are grounding this point or we are applying a 0 voltage, this one, upper threshold voltage equal to minus of lower threshold voltage. And here, if we select the upper threshold voltage equal to minus lower threshold voltage, a symmetrical square output will be getting. You will be getting a symmetrical square output obtained at the output of the Schmitt trigger. Now, in order to find out the instant at which this transition is taking place, that is the instant at which this point is equal to Vm sin theta. Therefore, this point happens when Vm sin theta equal to upper threshold voltage VUT, or it is equal to Vm sin theta equal to upper threshold voltage, or sin theta equal to VUT divided by Vm, or theta equal to sin inverse VUT divided by Vm. At this instant of firing, angle, at the instant of angle theta, here you will be changing, the transition is taking place plus Vsat to minus Vsat. Therefore, this is the angle sin theta which is equal to VUT divided by Vm, or theta equal to sin inverse VUT divided by Vm. Now let us see a problem on the Schmitt trigger. The Schmitt trigger circuit is given. That is, in a Schmitt trigger circuit, the R1 and R2 are given. R1 equal to 50 kilo and R2 equal to 100 ohms. These are given, and V reference voltage is given as 0. This is given. This is grounded, and the input voltage is whatever this input voltage you are applying, 1 volt peak to peak. 1 volt peak to peak means that it is equal to 0.5 peak value, 0.5 sin omega t. 1 volt is the peak to peak value, sine wave, and the saturation voltages are plus Vsat equal to plus 14 and minus Vsat is equal to minus 40. Determine the threshold voltages, that is upper threshold voltage as well as lower threshold voltage, because the equation for upper threshold or threshold voltage already we had derived. It is equal to Vsat into Vsat into R2 divided by R1 plus R2 plus V reference into R1 divided by R1 plus R2. This is the upper threshold voltage. Similarly, lower threshold voltage also derived. And if you consider that this reference voltage is ground, or that is 0 voltage, then we are derived it is upper threshold voltage equal to minus of lower threshold voltage, which is equal to Vsat into R2 divided by R1 plus R2. Therefore, Vsat is given as plus 14 into R2 100 ohm divided by 50 kilo ohms, here 50 kilo ohm plus 100 ohm, which will be getting 28 millivolt.
Therefore, upper threshold voltage equal to 28 millivolt and lower threshold voltage is equal to minus VLT. VLT equal to minus VUT, which is equal to minus 28 millivolt. Therefore, when this is equal to zero voltage or reference voltage, upper threshold voltage is equal to minus of lower threshold voltage, and upper threshold voltage will be calculating 28 millivolt and lower threshold voltage equal to minus 28 millivolt. Second problem, a Schmitt trigger with the upper threshold voltage, it is given as 0 voltage and hysteresis bit is given as 0.2 volt, and that converts a 1 kilohertz sinusoidal, this is a 1 kilohertz sinusoidal of amplitude 4 volt peak to peak 4, meaning that this is equal to 2 volt and this is equal to minus 2 volt into a square waveform, that is converted into a square waveform. Calculate the time duration of the negative and positive portion of the output. Therefore, certain portion it will be either negative, mean it will be marked as 0 as a low, and when it is high, what is the duration T1 and T2? That is the question. Now coming to this problem here, upper threshold voltage is given as 0 voltage and the hysteresis width is given as 0.2 volt. Hysteresis width is nothing but upper threshold voltage minus lower threshold voltage. So that is given as 0.2 volt and VUT is given as 0 here. Therefore, lower threshold voltage is equal to, substituting in this equation, we will be getting minus 0.2 volt. Therefore, upper threshold voltage equal to 0 and lower threshold voltage equal to minus 0.2 volt. Then you have to calculate what is these are the instants, and then you can calculate what is T1, and if you calculate the total time period, T minus T1 will give T2. Continuing the previous problem in which this is the input that is given and you are asked to find out what is the T1 and what is the T2, and we have calculated what is the upper threshold voltage is given as 0 and the lower threshold voltage is, you calculate it is equal to minus 0.2, and then this is a minus 0.2 level, this is a minus 0.2. You are asked to find out what is this bit T1. In order to calculate the T1, what the method we are following is that this is the time period of the signal, which is equal, which you can calculate 1 by frequency. If frequency is given as, say, frequency T equal to 1 by F, or that is equal to 1 milliseconds. This is equal to 1 milliseconds. Now once you know the time period, this is equal to T by 2, or that is equal to 0.5 milliseconds. Then if you add this time, that is the duration at which this period, theta, if you add, then you will be getting total T1. Now in order to calculate the theta, then what you have to compare this one, the lower threshold voltage equal to minus 0.2. Therefore, the lower threshold voltage is equal to, here the voltage, input voltage is equal to Vm sin pi plus theta. Vm sin pi plus theta equal to minus 2. From this equation, you can calculate what is sin theta, which is equal to 0.1, or theta can be written as 0.1 radians. Therefore, this theta, that is theta means from here to here, that will be getting 0.1 radians. Now you have to convert this radians into seconds. That is done here. Therefore, omega into t theta it is multiplied, or 2 pi into f, that is a frequency, to omega is converted, that into this time theta, that is you will be getting, that is equal to 0.1, and the t theta equal to, you can calculate what is t theta equal to omega t theta, which is here sin theta equal to 0.1. Therefore, theta equal to 0.1 radians. Therefore, time period is omega t theta equal to 0.1. That is, this is sin, that's equal to 0.1. Or then t theta you can calculate from this equation. You are converting this one into the corresponding time. Then you will be getting it is equal to 0.016 milliseconds. That is, from here to here you are calculating it is equal to 0.016 milliseconds. Now once you get this time as well as this time, already its t is calculated 1 milliseconds. Therefore, this is equal to 0.5 milliseconds. 0.5 milliseconds plus this time, which is equal to 0.016 milliseconds. Then you will be getting the total time T1, which is equal to 0.516 milliseconds. And in order to calculate this time T2, total time period T is equal to 1 millisecond. That 1 millisecond minus T1, which is equal to 1 millisecond minus 0.516 millisecond, which will be 0.484 millisecond. Therefore, this is equal to 0.484 milliseconds, and T1 is equal to 0.516 516 milliseconds. Next, let us see voltage comparator, widely using one, LM311. It is IC configuration is given here. LM311 pin out pin diagram is given, and of course here ground VCC, and here the inverting and non-inverting terminal, and here the output is given. Therefore, this is the pin diagram of a LM311 voltage comparator. This is a voltage comparator. It's an op-amp only, but this is specifically used for as a comparator. So therefore, let us see how an application of this comparator that is shown in this diagram. Same IC is shown here, in which it is the purpose is that when this is a comparator night light circuit, meaning that if during the night period this light has to glow, or it is marked as an LED. This LED has to glow during the night period, and meaning that during the day period this should not glow. Therefore, that's just how being implemented using a voltage comparator, just to show that one only. And in that one here, the inverting terminal that is equal to the terminal 3, and non-inverting terminal is equal to 2 here. And to the non-inverting terminal, you are applying a voltage to a potential divider, a potentiometer. The voltage is given to a non-inverting terminal. From a VCC, it is potential divider connection, and as you change this one, you can change this, or you can calibrate this voltage or this at the terminal 2, or say non-inverting terminal. And other terminals are, say here pin number 1 is grounded, and pin number 1 this is also grounded, and output is obtained at the pin number 7. And here 8 pin number 8 you are applying the VCC. This is actually that this voltage is equal to VCC, and here the output 7 output this output is getting, and from VCC and to this point you are connecting an LED, and the LED will be glowing when there is a ground voltage. When 7 is ground voltage, then there will be a current through this LED, and the LED will be glowing. The purpose is that during the night period it has to glow, meaning that during the night period this has to be made to 0. It's a ground voltage, then there will be a current and that will be glowing. Now let us see the working of that one. During the night period, the resistance of this one, this is a light detecting resistance, photoresistor, as it is the resistance value is a function of the light. During the night period, since there is the resistance of this one will be much higher, and this voltage will be much higher, or the voltage at the point 3 will be much higher than the point is already calibrated than the voltage at the point 2, meaning that the voltage at the inverting terminal is will be more than non-inverting terminal. And once this voltage is going more than this one, this will become low, or in this case that will be changing to the ground voltage, meaning that here is the ground voltage, means here a VCC is the ground, means there will be a current pass through this LED and the LED will be glowing. That is happening during the night period because this resistance will be lost, and this voltage drop, because this voltage drop is nothing but VCC is applied between this one. Therefore, that voltage divided by sum of this resistance into this resistance. As this resistance is more here, he will be getting more voltage at this point, so that once this voltage is going more than the voltage at this point 2, here output will become low, or output will become ground voltage, and at that time this LED will be glowing. Now during the daytime, this resistance will be less, so that this voltage is going low than this one, or here it will become high, or this won't glow, because once this is high, there won't be any current through this LED and it won't glow. This is just to show the application of a comparator, a voltage comparator for the night light circuit. That's only the purpose of this presentation in this slide. For say this is a voltage comparator IC, and this voltage comparator IC is used for a night light circuit, because this resistance is a function of the light that varies as the light intensity varying, and during the night period this resistance will be higher and you will be getting more voltage, and here it becomes 0, then this will be glowing. At daytime the resistance will be less, therefore this voltage will be less than this one, or meaning that here it will become high, or when it is high there won't be any current and it won't glow. Therefore during day period this won't glow, and during night period that will be glowing. That is called night light circuit using a comparator LM311.